everyone. Due to the scheduling issues with MCAS this week, I thought it would be a good idea to do a video on nondisjunction, which is objective 10 in your packet 12. It's a relatively simple concept that is the cause of chromosomal symptoms such as Down syndrome. I think you'll find it pretty interesting. I also think we can do it really quickly in a video. I'm going to use a new software program for the iPad called Explain Everything, so bear with me while I figure it out. Thanks. Okay, so nondisjunction is a failure of chromosome separation in anaphase 1 or 2. What this means is instead of either the homologous chromosome pairs separating or the sister chromatids separating due to the spindle fibers pulling them apart, that just doesn't happen. So if nondisjunction occurs in the first part of meiosis in anaphase 1, that means that the homologs don't separate. This should say homologs, not homologous, right here. And if this happens in anaphase 2 of meiosis, or the second division in meiosis, that means that the chromatids don't separate. And so both sides of the X will go to one side. And we're going to look at what this looks like in a minute. As a result of this, the gametes that are produced in meiosis will have an abnormal number of chromosomes, either more or fewer than they're supposed to. Normally, a nondisjunction event, a zygote or a fertilized egg that has a nondisjunction event very often will not become a baby. It's just what we consider not compatible with life. And that's why you can see here that 20 to 50% of miscarriages that people have are because of this issue, this nondisjunction issue. Depending on what chromosome doesn't separate, there are some syndromes that you might be familiar with that are compatible with life. In other words, there are some instances where that zygote can develop and become a baby and can survive and sometimes lead a very healthy life. So instead of having two sets of each chromosome, if you have 3, that's called a trisomy. And the most well-known example of that is Down syndrome, where individuals end up with 3 copies of chromosome 21 instead of only 2. There's also a case where you could have 1 chromosome instead of 2, and that would be called monosomy, or I'm not sure how to pronounce it, where you have 1 chromosome instead of 2. And I'm going to tell you about Turner syndrome, which is a one-of-a-kind chromosome abnormality on the sex chromosomes. So let's move over and look at a picture of this. So you can see here, this is an example of nondisjunction happening in the second half of meiosis, where your first part, I'll just use my laser pointer here, your first part of meiosis seemed to go pretty well. You can see here that the homologs, it's really ugly handwriting. The homologs do separate as they should in meiosis 1, but in meiosis 2, this little X didn't pull apart here. The sister chromatids stayed stuck together and both went to one side. What you can see is that means that when this cell divides for the second time, this cell right here is going to wind up with both sister chromatids for that. And this cell right here is going to have no sister chromatids for that chromosome. So while this side seemed to do okay, the left-hand side here ends up with gametes that are either have an extra chromosome or are missing a chromosome. So what I'd like you to do right now, assuming you have written down the notes from the text before, is to turn your page back 1 page to page 10. And I have a picture of page 10 here that I took a picture, and I'm just going to focus right now on the first one, the first half of that. And this image is going to explain for us what happens in this context of Down syndrome. So you can see here that we have our immature egg cell. And our immature egg cell has a
it's going to have 23 pairs of chromosomes, but we're really only focusing on chromosomes 19 through X. So we have 1, 2, 3, 4, 5 pairs of chromosomes in this immature egg or primary oocyte. Normally you would draw 46, but that would take up our whole egg. And you can see here that there's a little dotted line that goes around like this. That one's kind of ugly. Let me try again. So you should do what I'm doing now on your paper. Just trace that dotted line so you can see where the anaphase is going to separate these homologous chromosome pairs. So what you're going to do is then draw in your cells below, your cells right here, I want you to draw what chromosomes would be in this cell and what chromosomes would be in this cell. So you do it on yours and I'll do it on mine. I'm just going to zoom in because I don't have a nice pen like you do. So I'm going to have a chromosome 19, and these are still replicated, and I'm going to draw them how they would be in metaphase 2, right? And so I have 22, and I have XX. But I also have, this is, by the way, how we draw chromosomes, how we sort of note chromosomes. We draw a little X to show if they're replicated or unreplicated, and then we put the number of the chromosome. But as you can see from the top of this page, the non-disjunction occurred here at chromosome 21, so I'm actually going to have 2 21s in my cell. Sorry, I'm trying to learn how to zoom. So I need to put another chromosome 21 in here. And likewise, you'll see that the other cell, this one right here, is not going to have any chromosome 21. So I'm going to do X to the 19. That's how I sort of think of it in my head. Chromosome 20. And then I have no 21, so I'm going to go straight to 22. And then I have another X chromosome because this individual is female. So you should have this written in your paper as well now. So if I zoom out, you'll be able to see now the difference. We have our original primary oocyte here that divided kind of funny, and we wound up with 2 chromosome 21s on this one and no chromosome 21s over here. So then if we continue with meiosis, we can go down to here and zoom back in. This cell from up here is going to split. All of these chromosomes are going to line up in the middle, even my extra one. Actually, I probably should have drawn it right there. And those sister chromatids are going to split in 2. So what I end up with is unreplicated chromosomes, like chromosome 19, chromosome 20, oops, 20, chromosome 21, and then I have another chromosome 21, and then I have a chromosome 22, and then I have my X. Now in this cell over here, I'll have 19, 20, but I will have no 21s. I'll have a 22, and I'll have my X. So you can see how if this egg starts to develop and gets fertilized, that this baby will have an uneven number of chromosomes. So let's go back over to here. You'll notice in this image that this was our immature egg, or our primary oocyte, which you can see right here. And to the side is the sperm, the primary spermatocyte. And this primary spermatocyte is, pardon my gender normative colors, is not going to have a non-disjunction event. So you can see here that right here. It says normal meiosis 1 and normal meiosis 2, as opposed to our other side where there was non-disjunction in meiosis 1 with the 21st chromosome pair and then normal meiosis 2. So what I'd like you to do is just really quickly fill in your sperm cells with the correct number of chromosomes. And, oops, how do I erase that? And I will do the same thing here. Okay, so if I zoom in on here, I'm going to do X19, 20, and an X chromosome. And then on the other side, I'm going to do the same thing, but with a Y chromosome. And that's because the male has an X and a Y, and so when they pair up in metaphase 1, you have an X chromosome on one side and a Y chromosome on another side. And so that would mean that in this cell I have 19, 20, 21, 22, and X, and the same thing here. And then in these two cells, which came from this cell, we have 19, 20, 21, 22, and then the Y. And those sister chromatids separated, and that's why we have 2 of each. Oops. 19, 20, and 21. Now, what I want you to notice is that we now have an egg cell and a sperm cell. The other thing I think you should do before we move forward is just write somewhere on this half of the page, and I tend to do it on the side here, that what we're doing is trying to figure out how could a zygote have 3 21st chromosomes. And you're obviously going to be able to write smaller and better than me, so I'm just going to stop. Because 3 21st chromosomes is Down syndrome. And many people think it's Down with an apostrophe, but it's so Downs, like named after somebody, but I think it's actually Down syndrome. But you can obviously correct me if I'm wrong. One thing I didn't do is fill in my egg cells here with no chromosome 21, so you should make sure you do that, but I'm just, for the sake of time, not going to. So what you'll notice is that these eggs have, this egg right here has 24 chromosomes instead of 23. Right, it has 2 21s. And when this egg joins with one of these sperm cells to be fertilized, then our sperm and egg cell, which is what makes a baby, that baby, that zygote, is going to have 47 chromosomes, or an extra 21. And this is what we call a trisomy. That is what happens in Down syndrome. So, with that, okay, so now we're going to look at how is it possible for a zygote to have 1 X chromosome and 0 Y chromosomes. So you should probably write that on the bottom half of your page along the margin here. How could a zygote have 1 X and 0 Y? I would just write that right along here. I'm going to spare you my terrible computer handwriting. So what you can see, the other problem with this is that the drawing is wrong. So in this egg, we are going to have normal meiosis 1. So you should cross this part out right here and just write in that this is normal. The picture in the packet is wrong. And then in the sperm cell, we're going to have a non-disjunction event with the sex chromosomes. So we are going to cross out normal and say non-disjunction occurs on sex chromosomes. And you'll obviously be able to write that more clearly than I will. So what we're going to do is continue the way we did before. You're probably going to beat me, but let's just fill in our chromosomes on our egg. So we're going to have 19, 20, 21, 22, and an X. Oops. Undo that. And then we're going to have, we're going to have our 19, 20, 21, 22, X, and the same thing here. And I'm going to just, for the sake of brevity, move on to the sperm cell. So what happens here is that you have 19, 20, 21, 22, but then you have both the X chromosome and the Y. So you can see that once you go through the second round of meiosis, you would have both X here and both Y here, and the same thing here. Whereas this cell would have no sex chromosomes. Which is good because I wrote too big to fit them. And then when you split again, oops, 19 to 22, 20 and 21, doesn't matter. Now if we kind of zoom back out, let's again look at what would happen if we have this egg pair with one of these sperm cells. So, or actually one of these. These are different syndromes. So if this egg here pairs with a sperm cell that doesn't have any chromosomes, then that resulting baby will have Turner's syndrome. They'll have 45 chromosomes because they will have no Y. So this person will be female, and there are some certain traits associated with Turner syndrome that we can talk about a little bit later. There's another syndrome, which I believe is called Klinefelter's, which is when you have a trisomy on the sex chromosome, meaning you would have two, you would be XXY as opposed to X and nothing. So again, this is a trisomy, this would be a monosomy. And so these are two examples that you have Downs and Turner's of what can happen with non-disjunction and chromosomal abnormalities. All right, so I wanted to show you some of these syndromes, specifically Turner syndrome and Klinefelter syndrome. So Turner syndrome is when somebody has just one X chromosome, no Y chromosome, and no second X chromosome. So this is a monosomy, and we just wrote out how it would happen. And girls with Turner syndrome, you might not even know that a girl had Turner syndrome. Usually they're just a little bit smaller in stature. They look really young and sometimes a little bit underdeveloped in terms of like puberty. And there are some issues which you can see here on this little screenshot I took of Wikipedia. Obviously they have some reproductive issues, and sometimes there are other issues because the X chromosome is quite big and has a lot of genes that aren't related to sex on it. So sometimes it can have an issue with, you can see right here, hearing concerns and autoimmune diseases. But generally speaking, they can live pretty normal lives. The same thing is true for people with Klinefelter syndrome, which is when somebody has XXY, which is what I was just explaining to you earlier. Men who have XXY tend to have issues such as hypogonadism and sterility. You might, again, not know that somebody has this condition. As you can see here, the physical appearance isn't really that different. Men who have XXY chromosomes tend to have a little bit weaker musculature and strength, and they tend to be kind of tall. At puberty, they don't produce as much testosterone as other boys, so sometimes they look a little bit less muscular or have less facial hair, and they do sometimes grow some breast tissue, and so that can increase their risk of having some of those, some what's called gynecomastia, increased breast tissue, and a lot of times they have cosmetic surgery, and there's some fertility issues there. But generally speaking, these individuals are relatively normal and can have a really happy, normal life, and you would never know. But most chromosomal abnormalities are not quite so easy to live with. As you know, Down syndrome, those individuals can have a happy and normal life, but that's one of the only regular autosomal chromosomal abnormalities that really is okay. A lot of them, like I said before, result in a miscarriage. So that's all I have for this objective. I know it's been kind of a long video, and I appreciate you sticking with it, and I will see you in class.